Dimitrios Nikolopoulos is the John W. Hancock Professor of Engineering at Virginia Tech. He serves as a professor in the Department of Computer Science and also in the Bradley Department of Electrical and Computer Engineering. Dimitrios, thank you so much for taking the time today.
Thank you very much, Joe.
So to start, I'd love to talk about kind of what is the future of high performance computing look like right now?
Yeah, it's a good question because this has been very actively debated and discussed. There's no clear direction at the minute. So the field crossed a major milestone a couple of years ago where they built the first exascale or exaflop computers. So the computers that can do 1 quadrillion operations per second. Several of these systems have been built in the United States and elsewhere in the world. And that was certainly a major breakthrough, a major advancement in the field. Since then, there's not necessarily a clear direction where the next generation of supercomputers should be focusing on, let alone how they should be built or constructed. So I can think of two directions that are being actively debated and discussed. One direction is the traditional direction. So these are computers that are built to do very large scale simulations of natural phenomena, of physical phenomena, with very high accuracy, very high fidelity. So these are massive simulation machines used when people are unable to do a physical experiment. This has been traditionally the driver for the design and implementation of many generations of supercomputers over the years. And it's motivated, of course, by science and engineering, by our need to understand the world at the atomic level, by our need to simulate complex weather phenomena or climate phenomena with a very high accuracy. So that's one direction. That would be the traditional direction. The second direction, which is the more disruptive one, the more perhaps unconventional one, is supercomputers being basically AI machines, and specifically machines that are enabling AI reasoning and AI enabling technologies at an unprecedented level, right? Now, why are these two directions very distinct? There's one very simple scientific reason, right? Okay, so traditional supercomputing uses what we call high precision arithmetic, double precision arithmetic. So they use basically floating point numbers, numbers with many digits beyond the decimal point. And they're designed to be fast and efficient in processing those numbers, whereas AI has this interesting property where you can use numbers without the decimal point. So what we call reduced precision numbers. You can even use small integers, and sometimes you can even use just two numbers, 0 and 1, and still do meaningful AI processing, meaning building AI models that can reason and can do useful things. So because of this dichotomy, because AI uses low precision arithmetic and traditional high performance computing uses high precision arithmetic or double precision arithmetic, you have two very opposing design approaches, right? This affects how you design your processors, how you design your memories, your networks, right? So you have two different directions of how to design the supercomputer. It's not clear what direction should be followed next. It's not clear whether you should build the next generation of machines just for AI. So tune the processors, tune the hardware for very efficient training of extremely large AI models, right? And for very efficient knowledge extraction from these models. Or you go the traditional path, which is basically keep scaling up our machines as they are, our accelerators, our memories, and so on and so forth for high precision arithmetic, okay? So there's tension between these two directions. It's not clear exactly where people want to go, and it's an ongoing discussion.
Yeah. Well, I'm curious, is the uh, reduced precision of the AI direction, does that translate to reduced precision in the knowledge that we extract? Or is
No,
there still
that's the
similar
interesting
precision?
thing. Yeah, that's a very good question. It does not translate to reduced precision in knowledge that we extract. So AI can be, you can build very powerful, very capable, large AI models with what we call half precision, right? So I'll express it differently, perhaps, to make it simpler to understand, right? So you can encode a number in a computer using 64 bits, 64 binary digits, right? But you can encode a truncated version of the same number using 32 bits or 16 bits or 8, right? Traditional high-performance computing uses 64-bit numbers, as many bits as possible, so that we can pack very too many decimal digits past the decimal point, right? But AI can work very well with 16 bits or even 8 bits and can still produce very useful models and can still build very large models with this with high accuracy. So that's the one of the beauties of AI, I guess, right? Okay, in terms of the technology used underneath AI is that it can work with very low precision, very low arithmetic precision. But then think, if you put yourselves in the shoes of a processor designer, processor designers right now, your NVIDIA and your AMD and your Intel and whatnot, they invest a lot of hardware real estate in supporting double precision arithmetic, high precision arithmetic. And they say, well, if AI is going to take over as a workload, if AI is the only workload that we should be meaningfully supporting, we can just do away with all this hardware and use our entire silicon capacity, our entire hardware capacity to do very fast, extremely fast, much faster, reduced precision arithmetic, which by definition is faster. You work with smaller numbers, you fetch less data, you process them much faster, you can do more parallel processing and so on and so forth, right? So the dichotomy there is, should I build machines and processors that support double precision, as I have been doing for the last 30, 40 years? Or should I just do away with it and say, no, my machine is solely designed to support AI, in which I can live with reduced precision, so much faster processors doing AI training and AI inference.
So you mentioned the design of the processor and the hardware real estate. Is it the case that AI processors are smaller spatially, and is that a reason for
Yeah, that's a
like
good question.
do they
Yes.
scale with less space?
Yeah. Yeah, it's a good question. So I remember many years ago, one of my mentors used a nice analogy there. The silicon that we use, on which we're building our processors, is like very expensive real estate, right? So you have to be very careful about what you put in its place, right? Or how to use it, how to make the best use of it. Now we have silicon and processors where we can pack hundreds of billions of transistors, right? So capacity is not an issue. It's how you use this capacity. Whether you use this capacity for double precision arithmetic or whether you use this capacity for single precision or low precision arithmetic. So it's not the case that we're building necessarily smaller processors in terms of their capacity or their power. It's the case that we use this extreme capacity that processors already have in a different way,
Hmm.
right? Now, that said, the fact that AI can be supported very well with reduced precision means that you can support AI really well on your smartphones, on your watches, right? So it opens up these opportunities for AI to be supported and improve its services and its capabilities also on consumer devices, right?
Hmm.
But the technologies that we use in consumer devices are not entirely different from the technology we use for supercomputers. People think that these are two very different things, but the underlying technologies, the fundamental technologies, are very similar. It's just a scale, right? And the power that these devices consume is very different. The capacities are very different. So I guess that we're not going to see smaller processors, I think, right? We're going to see a different way to use these processors.
Hmm.
So if you take a processor from NVIDIA and you dedicate its entire hardware for low precision arithmetic, it will be orders of magnitude faster. It can pack orders of magnitude more numbers, right? It can fetch from memory orders of magnitude more numbers per second, let's say, or per millisecond. So you have all this additional computing power because you're working with smaller numbers.
So you've mentioned these two paths, a traditional path and a disruptive path. What's the decision right now? Is it Do we have to make a decision? Can we go forward with both
Yeah,
paths, or
yeah.
is there a
So
reason to
yeah,
push for one over the other? How do you think
yeah,
about that?
yeah, yeah. Very good questions. The reasonable approach here, I think, is to follow both paths because you still have the need to support traditional simulation-based, simulation-driven science and engineering. We still need these machines to simulate complex systems with high accuracy. That's still very important in many fields, in physics, in chemistry, in medicine, right? So this cannot just go away. The question is because our supercomputers are built primarily from commercial components, right? Commercial processors, whether these commercial vendors, the vendors of this process, are going to focus their efforts on the traditional supercomputing kind of applications and how much versus the more profitable or the more interesting, you pick, what you want to call it here, direction of building AI processes, right? So supercomputing has been based on partnerships between stakeholders like governments and national labs or technology companies that are not computing companies, and then the actual computing vendors who build the processors and the hardware and the memories and the networks and so on and so forth. And this partnership has been based on an understanding of what are the key applications. But if the same vendors invest most or the vast majority of their resources into AI, right, then this creates a tension a little bit, right?
Hmm.
Uh, so that's one way to look at it. The other way to look at it is how can you build a machine that does both well,
Hmm.
right? Okay, so and this I think this is a real scientific challenge, right? So this is a real challenge for us computer scientists and computer engineers. How do you build a machine that is a supercomputing class machine, so extremely fast, right? And equally good at AI and traditional supercomputing applications, right? So how do you do that? And when you scale it, how do you scale? How do you sustain it? So these are very good questions. There's no clear answer right now about how this machine should look like, and I think that's a very interesting question, right? That we will be facing in the next few years.
So you said that the people that or the companies that make processors may just follow the most profitable path, which would lead them to creating um, more AI.
Yeah,
They would take
yeah,
the path that towards AI.
yeah,
Is there a but you also mentioned like that a lot of times this is a partnership with government. Is there
yeah,
a need for a government policy to say we still need to continue to guarantee that these traditional processors
yeah,
are created, or is it okay to just let the market do its thing?
yeah, yeah,
What do you think about that?
yeah. So it's a complex landscape. Currently, the government and the stakeholders, right, are discussing, thinking about which way to go. But basically, the question is, should the government itself invest in building more supercomputers? Or should it rely on the hardware that is already available for these companies? We call them hyperscalers, right? So the likes of Google and Microsoft and Amazon, of course. So they have immense computing power. So there is a legitimate question there. Should the government invest on building our own supercomputers from places like national labs and so on and so forth? Or should we rely on the hardware that is already available, the massive volumes of hardware that is already available by the likes of, the hyperscalers? And this is where the tension comes, right? Okay, so traditionally, historically, there has been funding and investment by the government in building supercomputers in partnership with hardware vendors, of course, but you have specific supercomputers built in national labs, Department of Energy labs, Department of Defense, and so on and so forth, right? The question is there still a need for building those machines, right? Or should we perhaps think about different partnership models where the hardware is not the hardware of the government anymore, but it's basically the hardware owned by the hyperscalers, and then we run on this hardware. We use this hardware basically for supercomputing applications, right? It's unlikely that the need for custom supercomputers will go completely away, but it might be the case that this need is slowly diminishing,
Mm.
right? And people figure out other models to use the, again, existing huge volumes of hardware that's available from these companies, right? With meaningful partnerships with these companies, right? To do the same kind of work. So there will be a tension down the road. I think there will be a tension between all these machines that have been built with federal funding and support over the years, and those commercial, let's call them machines, which are way more powerful, way more scalable, have way more resources, right, in terms of their maintenance and their scaling and their future sustainability, right? So what's the right model here? I think it's an open question, right?
Yeah. Well, maybe this is more of a philosophical question, but you mentioned like some of the traditional things that we or the things that we use supercomputing for is like understanding the complexity of our natural environment and doing a lot of research. Um, does it does it make sense for the government to continue to procure and build its own supercomputers for the national labs, like you mentioned,
Yeah.
so that that research can be done independent of the private sector,
Yeah.
or does it mean moving forward we just rely on the hyperscalers?
Yeah. So um, it has made sense for many years for the government to build its own machines, right? Okay, there are certain applications that are very important. There are applications that affect the entire world population, if you will, right? And I'm not talking just about the advancement of science here. I'm talking about climate modeling. So these are very important applications. Now, the question is the government investment necessary or not? I think, right? There's clearly a necessity to support these applications, but we're talking about the government investment in the hardware, right? Or does it make sense to find other models to work with partners, vendors who have existing hardware and can perhaps support these applications? And what are these models? What's the most cost-efficient way? What's the most secure way? Right? What's the way that meets all kinds of regulations and constraints and so on and so forth? If the applications use very proprietary data or other, they have other constraints like the security constraints, what's the best way to do that? I think that it's more of a matter of what is the model um, of of building these machines either physically or virtually from existing hardware from vendors, right? Rather than the clear need to keep supporting these applications and improving those applications, improving the software and using these applications for moving science forward. So I think that the need is clearly there. The big question is, should we invest on building our own hardware? Let's say you're the government, right? Or should we partner with others for this hardware?
Yeah.
And there is no good answer. I mean, even if you ask this question at the lower level, not at the highest possible levels, but at the levels of researchers like me, for example, right? There's not necessarily clear answer, right? I can use in my research some supercomputers, but I have constraints, right? I may be waiting a very long time to access them and so on and so forth. Or I can use immediately off the bat virtual Amazon resources or Google resources, but I have to pay, right, for those. So what's the best way to move forward in my science? It's not clear to me either, right? What's the most cost efficient way? Should I sacrifice time but get free resources, or should I accelerate my research but pay for my resources?
Mm.
So the dilemma that I am facing as a researcher, or my students are facing, should I use Amazon Cloud or Google Cloud or the high performance computing machine of my university or some federally funded resource? The same dilemma, you can see it happening at higher levels, right? So do we have our own privately funded resources, right, that we build ourselves? Does it make sense for us? Does it serve our purposes and our needs, or should we use the existing resources? There's no good answer, I think, to this question. Some people think that it's very expensive to use commercial resources, but they're available. They're very well maintained.
Hmm.
They're growing really fast. They have the latest technology, right? So there are trade-offs there that we face.
Yeah. Well, I want to switch gears just a little bit and ask
Yeah.
you about uh, in-memory databases. What are in-memory databases? What do they do, and why are they important?
Right. Yeah. So in-memory databases refers to a technology that has matured, I think, over the last few years, and refers to the fact that traditionally databases have been using hard disks, right? Okay, to store the data. And historically, fetching data out of disks themselves being for many years mechanical components with rotating plates and whatnot, was very slow. Over the years, because we were able to build these large clusters, right, of computers, we thought that, well, it might be useful and faster and more efficient to move as much of the database data into the memories of these computers, out of the disks into the memories, the random access memories, as we call them, right, which are much faster to access. And in the last decade, at least, there has been a proliferation of new random access memory technologies, um, which are what we call non-volatile. So they have the property of the disk, which is that you can retain the data if you are if you power off, right? If you turn off the machine, you can still retain the data. But they also have the advantages of other random access memories, which is that they're much faster to access than disks, right? So you have a new range of technologies right there in the middle between what we call RAM, random access memory, which has been traditional volatile memory, and disks, which has been traditional non-volatile memory. So there's now this range of new non-volatile random access memory technologies, hybrids, if you want, between the two, which they can hold a lot of data. So loading database data in these technologies is way faster. It's very efficient. Our personal systems have almost eliminated actually disks, right, from their technologies, but even at the level of large scale systems and databases, you see that most of our data now are held in devices that allow random access in memory, right? So and I think this is a trend that continues right now, is growing. There are interesting new technologies and devices with more capacity, better speed properties developed. And it's a technology that certainly has taken over the world over the last few years. Okay. Now, some people ask an interesting question here, which is like, is there still a need for disks, right? Or is there still a need for even slower media like tapes? And the answer is yes, because there's so much archival data, right? So for day-to-day use, we have been able to replace the hard disk with non-volatile memories and flash drives and whatnot. But for archival purposes, if we want to retain historical data, huge volumes of data, we still need disks and we still need tapes.
Hmm.
So if you go to a place like, for example, CERN in Switzerland, right? So you'll see a huge system of tapes. And you will be wondering, but why are these people are using tapes? Don't they use the state of the art? They use the state of the art, but they need the tapes because they have so much archival data that they cannot get rid of. They need the data still for their own work and their own simulations and analysis. So they cannot yet throw away the data. So if the data gets produced at rates of terabytes per day or petabytes per day, you have to archive them somewhere, right? And it's not going to be in memory. You don't have enough capacity in memory for this. So you still have need for disks and you still have a need for tapes.
So is that a matter of converting the archival data, or is it just that it exists in a different way? Why do you still need or that it is created in such volume that you can't convert it quickly? How does that work?
Their volume is massive to fit in memories,
Hmm.
right? Okay, so in what we call memories, so in this faster media. So there's a volume problem and there's a need problem, which is that your archive data because you might still need the data, right? Okay. There are processes and protocols in place in many organizations to eventually discard data, right, after a certain number of times. But in certain areas, you really need the data,
Mm.
right? You may have to do comparisons with all the data. You may have to go back to all the data to verify assumptions or dispute assumptions and so on and so forth, right? So it's a volume problem, right? And it's a problem that sometimes we have a lot of data that we're not really yet certain that we can get rid of, right?
Mm.
Before we draw final conclusions, right?
Yeah. So I also want to ask you about parallelizing compilers.
Hmm.
What are parallelizing compilers? What do they do, and why are they
Yeah.
important?
Yeah. So this is a topic that is very close to my heart because this is a technology that has been dormant, right, for a number of years now. But critical technology. So let me say what the parallelizing compiler is first, and then we can have a longer conversation about this. So a compiler is basically a program that translates another program written in a high-level language, like I don't know, Python, let's say, or Java, to a machine language, to a low-level language. Okay, and traditionally compilers have been there to help programmers uh, program at a high level, which is intuitive and understandable to humans, but then generate code that is very efficient when run at the machine level, right? So they were effectively hiding the complexities from machines from programmers. So you program using your high level language, you have your algorithms and so on and so forth, and this magical tool called the compiler is going to generate machine code, binary code. And it's going to do it very, very well, right? Meaning that it's going to be correct and it's going to be efficient and it's going to be safe and so on and so forth. So that's the traditional compiler, right, to this date, from the late 50s or early 60s to this date. A parallelizing compiler is a compiler that takes code written in a language, again, and um, generates code written in the same language, but able to run across multiple processors, right? And why it's equivalent code, so the code should do the exact same thing, but it should be able to run on many processors, right? Why run on many processors? Well, two reasons. One is you can write this code faster, so you have a fixed problem that you solve with your code, and you split the problem between multiple processors, so multiple entities work together to solve the problem. Each entity solves a part of the problem, and together they finish the job faster. Or you can use many processors to solve a bigger problem, right? So when one processor can solve a problem of up to a certain size, maybe 10 processors can solve a problem with 10 times the size. So both cases very useful, both cases very practical. So that's a parallelizing compiler from 10,000 feet away, right? Now, the challenge with parallelizing compilers has been that taking code that has been written for a single processor and transforming code that runs correctly and efficiently on multiple processors is very hard. It's a very, very hard task, which can be automated in certain scenarios, but cannot be achieved in general for all kinds of programs, for all kinds of languages, and for all kinds of systems, right? So the curse and the blessing of parallels and compilers has been that, let me start backwards a little bit. So they have been studied a lot in the late 70s, 80s, and early in the 90s, but it was a small community studying them. It was a niche area. It was an area that was primarily studied by high performance computing people because they were very useful for supercomputers, right? But what happened was that in the late 90s and the early 2000s, all the processors started adopting new designs, which were very parallel, right? So you had the one single monolithic processor, and all these monolithic processors got replaced with chips that had 4 processors on them, or 8 processors on them, or 16 processors, what we call multi-core processors, right? So the chip itself would have multiple processing engines, and you would absolutely need parallelization to use these engines efficiently. And that's when parallelizing compilers came back, right, as a potentially very useful technology, right? Because they would be able to avert a software crisis where you would have lots and lots and lots of human programmers trying to convert sequential code into parallel code and do this automatically, right? So there was a flurry of new activity, right, into parallelizing compilers. Um, it has produced some interesting results, but the reality is that you don't have, computationally speaking, algorithms that can safely parallelize any program, right? And prove that the produced parallelized program is correct, right? And of course, efficient, but primarily correct. So there's a correctness challenge there. Many programs have been parallelized efficiently. AI has been parallelized brilliantly, right? There's no problem parallelizing AI code, right? So all these large language models or these fantastic AI models are built on top of software that has been parallelized nicely. But there are still some other classes of software and applications that are hard to parallelize. Okay. So parallelizing compilers have been this tool that has been seen with a lot of promise, right? In the past, the research on on these compilers has produced some fantastic results, but there are some fundamental limitations that still require human intervention, basically, to do parallelization. Um, so these days, we don't have exactly auto-parallelizing compilers. We have compilers that do limited forms of parallelization. So there's a class called vectorization, for example, where you take code that is what we call loops, and you convert these loops into vector instructions, right? So you process vectors. So this has been there. It's there. It has been there for some years. It's a good technology, right? It applies very well. Auto parallelization still remains kind of elusive, right? Okay, if you look around for the very best commercial compilers, if you look at GPUs, for example, there are no tools. I'm not aware of any tools actually that take code and magically convert it to GPU code, to NVIDIA code, right? Okay, you still have to use libraries and write the code for the specific machine, right? So the holy grail of auto parallelization has been elusive, right, for many years. We run into very hard, computationally speaking, problems or impossible to solve problems, right? But through studying these technologies, these compilers, we were able to advance our knowledge of how we as humans can more efficiently, more productively parallelize code. So we have this middle ground now where we don't have full automatic parallelization, but we have a helping hand for parallelization. So humans can fairly quickly now start from sequential code and arrive at parallel code with the assistance of a compiler, but not with a compiler doing the whole thing automatically, if that makes sense. Okay.
Well,
Now the question is close to my heart because I worked in this area. And I decided to stop working in this area at some point because I was hitting these very hard problems that I couldn't see how, right? But I stayed in this idea that maybe the compiler cannot solve all your problems, but it can help you. And a lot of my early research and my most successful actually early research has been on, okay, so can we have a middle ground where the compiler is not doing all the work for the human, but helps the human? And we had a lot of good results there.
so just a point of clarification, when you say auto parallelization
Mhm.
is the holy grail, is
Mhm.
that using AI to do the parallelization, or is that writing
Right.
an algorithm that will do
Right.
something automatically? Is it like
Yeah.
figuring out, or a human figuring it out and then the auto
Mm.
by algorithm it happening, or is it that AI is
Yeah.
doing something?
Yeah. So for many years, it has been algorithms, right? Okay. So we have been looking for algorithms that take a program, break it down into components and try to parallelize the program, right? And try to produce an equivalent program. So we're looking into algorithm, automated, mechanistic kind of processes. With AI, theoretically, you could try to attack and tackle the same problem, but the conditions that you have are no different, right? So AI cannot overcome the fundamental. So I'll give you an example of what I'm talking about, right? So when you run a program, you don't know what numbers the program is going to process. Sorry, when you write a program, not when you run a program. When you write a program and when you compile a program, you don't know what inputs the program is going to get. You try to write the program for any possible input, but you don't know the actual inputs, right? That's a very simple problem, right? So you write a program to sort numbers, you don't know what batch of numbers you're going to get, right? But if you knew, right, then you might be able to write a more efficient program or a parallel program, right, that does it efficiently. So, or if you knew how program uses memory exactly, right, you would be able to write the code. So we cannot statically, when we compile programs, know all the information about what's going to happen when the program runs. And especially we don't know the inputs to the program. So that's a major problem. It's a major barrier, right? So there has been a lot of work, right, in trying to, and we know that a lot of programs have this structure that no matter what the input, you can still parallelize them. But there are still some programs where, you don't know whether you can parallelize them or not based on the input, right? So that's an example of a problem that is very, very hard to solve with an algorithm. So, and even with AI, you still don't know that. I mean, AI cannot possibly fix this problem, right? So the inputs to a program are something that you don't know in advance, basically, right? So I don't think that AI is an answer here. I think that AI is just another helping hand, though, right? So I think that AI can again help human programmers accelerate this very difficult, laborious process of parallelizing and optimizing code. And we're looking into this problem ourselves as well in our lab here, but it's really helping hand, right? So it's basically you can use AI to scan all this knowledge, scan all this code that is out there to find samples, examples, templates that maybe can help you, but you cannot use AI to automatically or automagically, right, solve the problem because the problem hits a very foundational limitation of computing.
Hmm. So I want to ask you about data stream processing systems as well. What are data stream processing systems?
Yeah,
What do they do and why are they important?
yeah. So when we talk about data streams, we talk about any system that receives data over a network at a very high speed, needs to scan this data and do something with this data, and very quickly move on to the next batch of data. So this is the notion of streaming, right? So you have a stream of video frames, you have a stream of music, you have a stream of financial transactions, right? So you're talking about these kinds of programs, right? Systems where these streams have a very strict regime, right? So you receive a transaction, let's say, you have to analyze it, you have to process it, and you have to quickly move on to the next transaction. So streaming has been there for many years, right? So it's something that has been supported for many years. The challenge over the history of computing has been that streams have become faster and faster and faster and faster, right? So you started running into cases where you had to have a stream of data and you have one part of the stream that might be, I don't know, several megabytes of data, maybe sometimes, and you had only a few milliseconds to process it, or even worse, right? One extreme scenario that I think you might be familiar with was in financial transactions when you do these high frequency trading transactions, right? So you have to basically take a decision, right, and do the transaction within the time span of a microsecond, maybe, right, or right less than a microsecond even. And doing the transaction per se is not very expensive, right? So I think that with computing power, you can do it, but making the decision on the data can be expensive, right? So you receive some data and then you say, for example, okay, let's assess the risk of this transaction, right? Assessing the risk is another program, right? Another, right, which can take a very long time. But your challenge here is that time is money and time is precious. So you still have only this few or even handful of microseconds to make your decision, right? So you have stream processing systems where you have these extreme performance requirements where within milliseconds or microseconds, you have to actually make a decision. Another good example I can give you from from years ago is in racing, for example, in Formula One, where they process very fast streams of data continuously, and they may have to make decisions on strategy, on how are you going to approach the race going forward, and so on and so forth, right? And they use very advanced computing systems to do stream processing, right? Because the data arrives at very fast speeds, right? And you have only milliseconds or microseconds to make a decision, which can be critical. So these are stream processing systems. I think what has happened over the years is that people have realized that they need high performance computing technologies, right, to process streams efficiently. And again, these technologies, although they have similarities with traditional supercomputing, they are also very different in the sense that, first of all, they connect to the outside world. They're not a standalone supercomputer, right? So they receive data from the outside world, right, over a network. And then they respond to the outside world as well, and they have to do that immediately. So a traditional supercomputer is a machine that crunches numbers for hours or days, or right to arrive to a conclusion, right? With stream applications, you don't have this luxury, right? So you need to arrive at that conclusion within a few milliseconds or within a few microseconds, right? And that's very challenging. So you need some different thinking about the design of the systems. You need very fast networking, and you need very fast ways to move the data through the system, right? And maybe your processor is not necessarily the most important bottleneck or the most important consideration here. What's really the important consideration is, can I move the data into and out of the system within microseconds?
Yeah.
And this is challenging, and this is something that has been researched, is still very actively researched, and still a very interesting area.
Yeah. Well, my last question is maybe more general. How is the advancement of AI influencing your research right now?
Ooh, in many ways, right? So AI is an enabler for sure, right? Okay, I am not neither a harsh critic of AI nor a big advocate of AI, right? So I think it's a major enabler, right? You have these tools where you have the ability to scan through massive volumes of literature and prior work and code very efficiently, right? And research has this component. And if you think of the history of research, we started doing research in libraries, so you have to actually travel to go to a library many centuries ago, and go to a monastery or somewhere, and then get into the library and then spend days and nights looking for the books. And over the years, technology, computing, networks, the internet, and so on and so forth sped up this process, right? So our process of searching for information and finding the information we need to do our research, right, and to advance our research has been accelerated and accelerated. And AI is a major catalyst in that.
Mm.
So that's a good thing about AI. The question is whether AI can also do more things in place of the researcher, right? And I'm not well positioned to answer this question, right? I still see AI currently as a good assistant, a very powerful assistant that can help improve the productivity of the researcher, the focus of the researcher. Um, uh, Replacing the researcher is it's a whole other question, right? Research still, in my view, and maybe I'm a little bit idealistic here, Joe, but in my view, it's still a process of not just discovery, but also creativity, right? Genuine intuition and genuine ideas,
Mm.
right? Uh, and this human intuition is very hard to replicate with AI, right? And if you even in engineering, where people in engineering they have trade-offs that they face, so they build a system and they have a cost trade-off and a performance trade-off and a usability trade-off and so on and so forth. This is where human creativity shines,
Mm.
right? This is where, the human is able to come up with a solution that is elegant and is functional and it's working and so on and so forth. I'm not sure if AI is there yet. Okay. So I appreciate the help I get from AI. I do use AI tools a lot, right? Happily, I'm not sure if AI is in a place to replace this intuition and this insight and this creativity that humans have in the research process.
Yeah.
So very good tool, excellent research assistant, virtual research assistant. Not sure if, AI is the researcher yet.
Yeah. Well, thank you so much, Dimitrios, for taking the time to share insights and wisdom. And I hope we can continue the conversation down the road.
Yes, thank you very much, Joe. I hope we do. Thank you.